Okay, we are recording, we are sharing the screen, and well, I want to show you this graphic. So this graphic is not working because we have this condensation risk, because we have an intersection here and another intersection here, and this can't happen. So I'm going to explain this again. So here we have plywood, the width, let's say it's 1 inch, and we're going to have something very simple. We have plywood, we have the vapor barrier. So far, imagine that we don't have a vapor barrier, so this is 0. Then we have the cellulose, then we have plywood again, and we can have an air barrier. If we don't have any, this would be 0. Okay, so that would be, we have 3 layers, 3 solid layers, plywood, cellulose, and plywood. And then we have 2 films, the vapor barrier and the air barrier. I recommend you always put this on every single detail. So inside the thermal insulation, you have it, and outside the thermal insulation, you have the air barrier. If you don't want to take it into account, type 0, and that's it. But do not delete this. So in every detail that you analyze, walls, floors, or roofs, so make sure, well, maybe in floors we don't need it, but in walls and roofs, make sure that you always have this vapor and the air barriers. And now we have to give the right numbers. So the thermal conductivity, this is wrong, by the way. So we have the plywood. What is the thermal conductivity of plywood? 0.75, yeah. So this is 0.75. And we have another plywood here, 0.75. The width, it can be ½ inch or 1 inch. Let's type ½ inch of plywood, and here ½ inch. Okay. What about the cellulose? We have to go to the thermal conductivity. There is cellulose here, 0.6. And what is the width? 8 inches. Okay, 8 inches. So this is plywood, 0.75. The width, ½ inch. Plywood, 0.75, ½ inch. And the cellulose, the conductivity is 0.6, the width 8. And the vapor barrier, well, thermal conductivity doesn't matter at all. So when we have something that in which the thermal conductivity is not important, okay, let's type 100, because this is a film. So it doesn't have anything to do with thermal resistance or thermal conductivity. What is relevant in these layers is the vapor resistivity. Okay. So if the width is 0, we don't have it. So most likely, if we have only plywood, cellulose, and plywood, there will be condensation risk. And is it, well, I don't like it, but well, here I have talked to people that it's not, for them, this is not important, or this is not quite important. And I can explain you why they consider that it's not important. If we take this screenshot and we open a PowerPoint, okay, this is the detail. There is a risk that condensation will happen here. And if that happens, we can make it more. Okay, so there will be water here. Eventually, not always, not 24 hours a day, but under some circumstances, we can have water here. And now we have to analyze the different layers that we have, especially where the thermal insulation is. So the thermal insulation, if we look at a graphic like this, is where we have the drop of the temperature. Okay, so look at this temperature here, and look at this temperature here. This should be the thermal insulation. Hello? So this is the thermal insulation. And we can see that by looking at the blue line. Okay, so if we have this temperature here, this temperature there, and this is the layer where the thermal insulation is. And I want to draw a rectangle here where the thermal insulation is. And I will use a shape fill, gradient, and I want something transparent and something like this. Okay, this is the cellulose. And we know that somewhere here in the middle of this cellulose, there will be some water. Well, I heard people say here, that say, okay, yeah, that would be an issue if it isn't, if we don't dry out this. If this cellulose is always wet, it's always an issue. But if we have air, okay, if we have an airflow here, well, it doesn't matter because we will end up drying out this. Okay, if the airflow is outside, this is for free. So eventually some water will appear here, but if we have airflow, it will dry out this cellulose. And okay, so this is an explanation. There's another explanation. They say, okay, imagine that we have a heating system here and there's a lot of heat going out. Okay, so this is the heat. Like this. And the temperature here is 70. Fahrenheit, and the temperature outdoors is 0 Fahrenheit. Okay, the heat will go out because we have a heating system here in our room. So eventually this heat going out will end up drying out this cellulose. Okay, so does it matter if some water can appear here? Well, it doesn't matter because eventually it will dry out. So that's an explanation. I don't like it. So in my opinion, we should prevent this from happening. Even though we can have this heat or this air drying out this. But you might find other opinions in which they consider that, well, it's not a big issue. Yeah, we have, it's better. This is, they claim that it's better the benefit that we create by using cellulose because it has a very low carbon footprint than the issues that we might have in our house. Well, I think we can get both. We can save the planet, and at the same time, we can avoid or we can prevent our risks or condensation risks in our house. So I will do both. Okay. So what can we do? By placing the right vapor and air barriers, I think it will be Good. And how can we do that? Okay, the vapor barrier and the air barrier are films. So we can say that it's very thin, 0.01 inch, the vapor in the air. Okay, so it's just a film. It doesn't have a thickness or a width. It's just a film. The thermal conductivity is not relevant. What is relevant is this: is the vapor resistivity. So the vapor resistivity should be higher always inside the thermal insulation. Look at, I use two different values. We can have 400 and to make something 4 million. Okay, if there is 400 inside and 4 million outside, we do have condensation risk. If it's the other way around, 4 million and 400, now we don't have this condensation risk. Okay, so in my opinion, this option is safer. There are some people that say, okay, it doesn't matter, so you don't have to use vapor barriers. Well, people here use air barriers outside because they, well, it's obvious because if the wind is blowing in winter, there will be infiltration issues. So they prevent infiltration issues with the air barrier. That's fine. But I would use the vapor barrier inside. Some people say, okay, using a vapor barrier is useless because the vapor barrier is so thin, you can scratch it so easily that eventually you won't have. Maybe you will spend your money requesting this vapor barrier in your thermal insulation, but people handling the panels will end up scratching this, and eventually you won't have it. Is it an excuse? Well, maybe. We are not in a perfect world, and accidents happen. And yeah, but the theory, and here we are studying the theory, is that if we have a vapor barrier inside the thermal insulation, we don't have condensation risks. And having condensation risks, yeah, you can say, if we have air outside and we have a heating system, it's inside, there is no, it will end up drying out. Yes, but what if we don't have this airflow, or what if, well, I don't know. But it doesn't mean that I'm right and everybody else is wrong. Sometimes it happens, but not in this case. But you have to think about it, and then you need to have your own criteria. If you are working with a company and you see what they are doing, and you request the vapor barrier, and you find out that 90% of vapor barriers are torn, they are not continuous, you can say, okay, I won't work with this company again. It's not that, okay, so this happens and having vapor barriers is useless. Well, I would make the decision of not working with that company again instead of not placing vapor barriers, which I think is the correct decision. But again, there are different options. This is the theory. And sometimes theory and reality are difficult to, it's difficult to combine the theory, the building science, and reality, because we have the human factor, and it depends on the quality of the workers, the construction company, the conditions we are working. It's not the, if we are working here in a comfortable conditions in a workshop, it's much better than working with this on site. On site, we can be cold, as Peter Joost told us a few weeks ago. But if we are working in a workshop and we get our prefabricated panel and we place it in the, it's easier having these kind of things. But it depends. Anyway, the theory is that using a vapor barrier inside the thermal insulation works. The reality is that even if it doesn't work, even if we have condensation, there's a likelihood that it's not important because we will end up drying out this. Yes, but again, this is not under our control. What if the clients there don't use the correct heating system And what if they place something here and we don't have this airflow that we are, well, we don't know. So that's why if we are on the safe side, if we have done things well, you know, I think this is the most important law in the universe, the Murphy law. If anything can go wrong, it will. Okay, so this is the most important law in the universe, especially in construction. So if you plan everything and there's something that can go wrong, it will. But of course, if you have created a bad detail and you are working with the wrong construction company, something will go wrong. Not something, but everything. Okay. So that's it. What is my advice? Use the thermal insulation. Inside the thermal insulation, place the vapor barrier. Outside the thermal insulation, place the air barrier. If you don't want to use it, just type 0 here, 0, then 0, and that's it. You don't have it. But at least if you want to use it, make sure that the highest vapor resistivity is always inside the thermal insulation. There's another option. This is what I was told when I was a student. Okay, do not use fibers, do not use glass fiber or wool or rock wool or whatever. Do not use wood fibers or cellulose. You have to use rigid insulation. So what happens if we use rigid insulation? This polystyrene. Okay, so for the polystyrene, the thermal conductivity is 0.17 and the thermal, no, the vapor resistivity is 300. Point 17, 8 inches, and this is 300. Okay, so as you can see, we reduce the condensation risks. And even if it happens, the rigid insulation can bear the water, so it's not affected by water. All the fibers, the glass wool, the rock wool, the cellulose, they are affected by water. And if they don't get dry immediately, they will stop being a thermal insulating material. With rigid insulation, first, we reduce the risk a lot. And second, even if we have some condensation, it's not affected. So that's why when I was a student, my teachers told me this, they showed me these graphics, I believed them. But now rigid insulation, I found out that it has a very high carbon footprint. Okay, so if we want to create sustainable buildings, rigid insulation or using massively rigid insulation is not an option. I would use this just, I can have 8 inches of cellulose inside, and then I can have a couple of inches of rigid insulation outside. Okay, so I'm not using 10 inches of rigid insulation. But there is always in roofs, again, in roofs, using cellulose, it's quite complicated because they are very exposed to water. That's why using at least a thin layer, 2 or 3 inches of rigid insulation, I think it's better. But if we combine 10 inches of cellulose, 2 inches of rigid insulation, from the thermal point of view, it would be perfect, and we will prevent these moisture issues. Okay, so this is what you have to do. First, we have to meet the passive house standards. I think all of you know how to do that. We need to make this above 50 and the roof more than 80. Okay, so you know how to do that. But there is something else in this course, and we have to evaluate the condensation risk. And for example, I have seen some okay, this midterm report. You have the table of contents, good. But if we analyze, let me go first to this. Okay, here I see this. Okay, there is no condensation risks. I like it. But if I analyze this, there are things that are not, or they are, well, we have the rigid insulation, 0.23, 0.23, 6, 2. Okay, so apparently this is already fixed. So with this rigid insulation, we don't have condensation risk. What if we use cellulose? Or what if we use cellulose? Because here we have 6 inches here and 2 inches and 6 inches of rigid insulation outside. Okay, what if 6 inches inside the concrete, it's a rigid insulation? Will we have condensation risk? We will have to find out. What if we have a vapor barrier here? Okay, so this detail works well because we don't have condensation risk. It's about 50 because it's 60, so it meets the passive house standards. But there's a third component. It has a very high carbon footprint. It's complicated. I mean, it's not just, okay, we have to check this in 3 aspects. The thermal resistance, meet the passive house standards, great. We don't have condensation risks. Okay, what is that's what we call the global warming potential. So the global warming potential is the amount of greenhouse gas that we emit to the atmosphere when we are manufacturing this material. Well, we are not talking about this in this course because you have there's an speedy course which is sustainable materials. So if you want to take this course as an elective, that would be great because you get to learn the global warming potential of materials. It can be construction materials or any other materials that you might find. But there are 3 aspects. Okay, so we are analyzing this from the thermal point of view with the R value, with the condensation risks, with this graphic, and finally we are not analyzing this from the global warming potential because we don't have time, but we could do it. But I think if you take this speedy sustainable materials, I think it's good because you will learn how to evaluate these kind of materials. So apparently the rigid insulation in terms of global warming potential is very bad and cellulose is very good. Okay, so okay, so I think this detail is good, and the rest of details I'll check in floors. Usually we don't have problems with floors. In roofs, this is above 80. Here you have a vapor barrier that it's 0, so it's you haven't used this. Okay, I think in this roof we have an issue. We have concrete, rigid insulation, 18 inches. 18 inches. It's 80, yeah. It's being sustainable comes at a price. We have to use 18 inches of thermal insulation on our roofs. And here we have the EPDM. Okay, this is not correct. I'm going to do this. If we analyze this roof, we have concrete, then vapor barrier, then rigid insulation, and EPDM. The width, it's 12, 0 because so far we don't have it. The rigid insulation is 18, and the EPDM is 1. Okay. But now we have to analyze the vapor resistivity. Okay, so let's analyze the vapor resistivities. Oh no, first the thermal conductivity. Concrete is 4.1, okay? The vapor barrier doesn't matter. The rigid insulation is 0.23, okay? And the EPDM it's 0.96. Olivia, I think this is yours. Where did you take this 0.96?
I got that off of Revit because I couldn't find it on this file.
Ah, okay, so you took this from Revit.
Yeah.
And the vapor resistivity from Revit as well?
I don't remember where I got that from.
Okay, great, but you took this from Revit. Yes, we have to be resourceful. If we don't find this material here and we have this material in Revit, let's do it. So the EPDM thermal conductivity is 0.96. Okay. So this is 0.96. The rigid insulation is 0.23. The vapor barrier can be 1 or whatever, doesn't matter. And then the concrete is 4.1. Okay, if you use Revit, because we are analyzing Revit, and in Revit we have materials and we have all these, okay, we can do that. But I don't think we have the vapor resistivity in Revit. So in Revit, we have to use this table. So if we are working with concrete, the vapor resistivity is 50. You have used 100. If you show me where you took these values from, that's fine. But I need to see the source of this. Is 500 or 50? The vapor barrier, well, vapor barrier is going to be always 4 million. The rigid insulation, the vapor resistivity of this rigid insulation is polystyrene. It's 300. And you have 10 here. No, this is not. It's it has to be 200, 300, something like that. And finally, the EPDM. EPDM itself, it's a waterproof layer, or it can be considered an air barrier as well. So I'm sure that can have a value of 400. Okay. So now, if we have this, I bet that we will have condensation risks. We don't. Yeah, we have. Okay. It's not that much because we have rigid insulation. And rigid insulation, okay, it works better when it comes to condensation risk. If we used here cellulose, the cellulose is, okay, I have to find out. The thermal conductivity, it was 0.6, and the vapor resistivity of cellulose, it's 10. Okay, so with cellulose, things are always worse. And when it comes to thermal condensation risk and even thermal performance, because now we have 34. Okay, so rigid insulation in terms of thermal properties and condensation risks, it's much better than cellulose, but cellulose it's better in terms of global warming potential. So if we are using cellulose here, that's fine. But for sure, we should be using a vapor barrier here. So if we have a thickness for the vapor barrier, 0.01, Okay, we eliminate the condensation risks. Even with cellulose. Okay. That's it. Then you ask me about conclusions. We are learning here, and we are working with conclusions. So what are the conclusions? So we have to ask some questions to ourselves. Different thermal insulating material. What if we use cellulose versus rigid insulation? In roofs with rigid insulation, we need 18 inches where is inch to meet the passive house standard. With cellulose, how many inches do we need to meet the passive house standards? With 18 inches, we don't need this. So it's 30 inches, not even 30. Okay, so how many inches do we need to meet the passive house standards with the cellulose? Okay, with rigid insulation, what about the condensation risk? And what about the condensation risk with cellulose? Do we need vapor barriers? Okay, so these can be conclusions. I have tried two different thermal insulating materials, cellulose and rigid insulation. What happened in the roof? If we want to meet the passive house standards, we need this. With cellulose, I don't know how many inches we need, but we need more. And what about the condensation risk? Sure, this one is going to be better than this one. Can we solve something if we use a vapor barrier inside the cellulose? Well, if we use this, at least we don't have the condensation risk. So why do we use cellulose? Because of global warming potential. And how can we evaluate this? CO2 equivalent okay. I'm sure I can find out. So by next year, I'm going to create a new column here, which is the global warming potential. or the CO2 equivalent emissions. Okay, so next year I will add another column here, and this is something that we need to know to assess this material in terms of, because when it comes to thermal conductivity and condensation risk, cellulose is going to be always the worst. So if you want to make cellulose to be good, we need to add this column here. Okay, so we're not doing this year, but next year I will. Okay, so if we look at this, this is the kind of conclusions that we need. And we have conclusions because we compare two different options, or three or four or whatever, but at least two. Okay, so if we have a result with this material and a different result with the other material, which material is the best? This one. Why? So this is the conclusions. You don't have to write 4 pages of conclusions, just bullet points of what we are doing. So if we are comparing thermal insulation, that will be the conclusion. But let's go over everything. So yeah, this is what I wanted. We have a building, we have something there. This is the justification. Why don't we have openings here, east and west? Well, because we have buildings, this is too narrow and there is no point in opening this. So that would be the answer. These are the spaces in plan and section. Here we have the sun path because I want to make sure that this is south and north oriented. The energy analysis, here we have all these materials. Look at this. You have used, this wall is 48. Yeah, it's slightly below 50, but it's quite good. I mean, with 48, we can even say that we meet the passive house standards. So the first analysis should have been with, I don't know, 25 or 30, something like that. Because if we look at the report, here, the peak cooling load is 96, the peak heating load is 27, and with a different option is 92 and 23. So it's not a big difference. Here you have this. Okay. So what are the conclusions? If we are talking about the passive house standard with option 1 and option 2. So this is option 2 and option, or is this option 1 or option 2? Okay, with option 1, we have 96 and 27. Okay, so that was option 2. It's 97 and 26. Okay, this is with without passive house standards, and this is with passive house standards. Savings. So what are the savings? It's 97 minus 92 divided by 97, and if we multiply by 100, this is the percentage of savings that we have here. Okay, so if I apply the calculator, this is 97 minus 92 is 5 divided by 97 times 100. It's 5%. But you have this because 5% is not a lot of savings. This is because you have used a first option that is too good. Okay, because here it's 48. If you had used a bad option with an R value of 25 or 30, the savings would be more. Imagine that you have a client and the client tells you, okay, this is my building. What shall I do? They won't do this energy retrofit for a 5% saving. This is not attractive. So you have to be honest to your client, and you have to tell the client, okay, you have a very good house. So if you want to save more money, you are almost meeting the passive house standards. So if you want to save money, probably tearing down your walls and building the walls again with a little more thermal insulation, it won't make a difference because the savings are only a 5%. But this is a conclusion. After analyzing this, you have this conclusion. It's not worth changing the walls because if we want to save 5% of energy, it's not worth it. Okay, so that would be one of the conclusions of this. What else? For the windows, you have always you have analyzed the low E triple glazing, so this is the best option. Where is the bad option about where is the double glass? For the windows, we should analyze a double glass versus a triple glazing. We have already talked about this. Okay, what about the therm analysis? You have the therm analysis. This is the detail, nice detail with 18 inches of rigid insulation here. You have analyzed that. And I think they are pretty good because you are wrapping this with thermal insulation, and then you have this double thermal insulation layer outside the building. So I think it's a good detail. What if you place this thermal insulation underneath that slab? What is the difference? And the difference is this. So here the R value is 95 and 10. What would be the R value if you placed the same amount of thermal insulation, but just here? I'm sure that it will work worse because there will be now we don't have a thermal bridge because we have a continuous thermal insulation. If this thermal insulation were here, there will be a kind of a thermal bridge, and I'm sure those numbers would be worse. But how much? Okay, so this is the conclusions of therm. Therm analysis. It's thermal insulation over versus under the concrete slab. Okay, and if you compare these two options, which option is better and why? We have to look at the R values. Option 1 and the R values. Option 2. Okay, so first, which option is the best? I think, well, whatever. Second, how much? So that's the difference between and we have to look at the R value. And then savings. Okay, so here savings are 5%. What are the savings? Maybe imagine that is 20%. If you have to do something and you save 20% here and 5% there, what would you do? First, I would do this. And then if I have enough money or enough time or whatever, I will try to do this. But first, that would be my first choice to retrofit the house. So this is the therm analysis. And Yeah, you have the triple glazing. I would need this because this is the thermal load through windows with the triple glazing. I would need the last selection, double versus triple glazing and savings. And that's it. And then we can, you had this, I like these schematics because here we can see that we have the air handling unit, and then you have the air supply, the air return, and then we have the heat recovery, and then you justify that we have the heat recovery. We can even do more. Okay, so what if we don't use a heat recovery here? Okay, so we can extend this as much as we can, but I think for you, with this, if you answer these questions about the passive house standards, about the therm analysis, the glass selection, and about the different thermal insulating materials, for conclusions would be more than enough. Okay, but we can have more. So if you're interested in analyze the difference between heat recovery and without the heat recovery, or a loose construction and a tight construction, but we always have to create conclusions. We always have to compare two different options, two or more, but at least two different options. Okay, next, I think this is yours.
Yeah.
Okay. Well, I like this because here you have a map and you showed me the location. That's important because in this case, okay, the first thing you have to tell me here is where the building is located. I don't know. Okay, so if it's in Boston, okay, let's where is it?
I think it's the
It's on the
yeah.
If it's in Boston, let me know at the beginning. And we have the orientation and location. So both things are important. And then we have the first analysis. The first analysis, the R value of the roof is 16. This is the first option.
Yeah, it was like 16.3 or something like that.
Okay, no, but I'm sure that when you are analyzing the second option, it's 84. So the savings should be great. This is 121 and 58. And for the first option, okay, yeah, so it's much better. And these are, you included the spaces now.
Yeah, I went in after and made some changes.
Okay. I want to see this because I want to see the overall analysis of the building with the total cooling and heating load, but I need this chart as well, looking at the area, because if we look at the spaces, yeah, so that should happen. The lobby should be always the biggest figure, because the lobby is the biggest space, okay? So this is 500, 400, that makes sense. And then we have the lobby, which is much more. So I would like to see this to check if it's correct or not. If I only see the total loads, there might be a mistake. So I need to see these spaces as well with the cooling and heating load. Here we have the windows. This is a low emissivity triple glazing. And the thermal analysis. You have compared two of them. And what have you done? So you compared two details.
Yeah, the EPS and the inside now.
Okay, yeah, so you did this. Okay, great. And here, well, there are two things that we can compare. We can compare the R value. I don't see the total R value here in your chart, but we can also compare the heat flux. Okay, so here, looking at this legend, the highest value is 2.1. And looking at this, the highest value is 16.7. Okay, so why? So this is worse than this because here the highest flux is much lower than this detail. And that's interesting because look at the amount of thermal insulation we have here and the amount of thermal insulation that we have there. So it's sometimes not about the amount of thermal insulation, it's about how we place this thermal insulation. Okay, so in this case, even with more thermal insulation, results are worse here than there. And you compare these two. Okay, so this is 22, and this is 2.1. Yeah, so clearly, yeah, because here, okay, so this is the thermal insulation underneath the floor slab, and this is worse. Okay, for the ventilation and infiltration, and then we have the glass selection with the triple glazing, and we have the solar heat gains. Oh, so this is from PV watts, and what is this? The northern and the southern orientation. Okay, actually, I need only this column because this is for the electricity analysis. So if you can crop this, and you can show only the solar radiation. And then we have this, yeah, you're using cellulose, and as it was expected, if you're using cellulose, we have a condensation risk. Do you mind including here a vapor barrier to try to avoid this? And show me both. The R value won't change, but the condensation risk, if you add a vapor barrier here inside the cellulose, I'm sure it will change. So you will reduce the condensation risk. And now the monthly performance. Apparently here, infiltration is the worst thing that is happening here. What is your... Okay, but it is already a tight building because you are using a 3. If this value is 3, it's good. Now, it can be worse. Okay, but basically the conclusions that I can reach looking at this graphic is that you have selected passive house standards for the envelope. You have a triple glazing. You have controlled the heat recovery with the ventilation. So what matters the most is the infiltration. And even if you have a tight construction. So this is a perfect building, or almost perfect, because you met all the standards. You have selected the best glass, triple glazing, low emissivity. You have selected a heat recovery. So on a perfect building, the most important heat loss is the infiltration. Oh, we can say, no, it's the window. No, it's the infiltration. So, in this area of the world, infiltration is relevant. In other areas of the world, it's the other way around. If you're living in Miami, I'm sure that what you want is fresh air. So you have all the windows open and you have air flows through the building. Here in winter, you cannot do that. And here you have in conclusions, passive house. Okay, so here you have two examples. I mean, they meet the requirements. The only thing, the conclusions, you're asking me, what about the conclusions? What can I write? Yeah, sometimes looking at the reality is easy. We can, okay, so yeah, it's a sunny day. Yeah, so what? How many sunny days do we have in winter? What is the temperature on a sunny day? Okay, so if we start asking questions to ourselves, then we can start reaching conclusions. If we just observe, we say, yeah, sunny day. Yeah, so this is glass. Yeah, so what? So this is glass. What is the orientation of this glass? It's north. North. Okay, do we need all this glass here? If we had all this glass, I would expect having the lights off. What's the point of having lights on if we have all this glass? Is it because we are using our building in a wrong way? What if I turn all these lights off? Can you work here? Okay, so let's work without lights because we are spending a lot of money because someone, the architect, decided to open this nice northern curtain wall. At least we can save energy by turning off the lights. And even we have light from this glass as well, so it's not direct light. But okay, so I don't think we need the artificial lights in this building. But probably if we didn't have this window here, we would need the artificial lights. And then, is it worth it? Is it worth the energy that we are wasting because of this northern glass? Does it make up the energy that we are saving by turning off the lights? Well, when we are here, we are working here. Okay, that would be a conclusion. But this is the kind of analysis that we have to. If you have a client, the client won't tell you what to do. They will hire you and they will pay you money, and that's more than enough. But if you can't pretend to be hired and say, okay, what shall I do? I don't know, you are the architect, you are the expert, do something, bring me a report, tell me what to do, whatever. But okay, so it's tough. I mean, life is difficult and tough, but eventually we will get paid, and that compensates for everything sometimes.